So here we are, and we're going to be doing exercise 17 now. And I want to show you how to do this one in Matlab. So why don't we go over to Matlab and try and do this in Matlab. What we want to do is we want to find the critical points, and then we want to classify them by looking at the eigenvalues of the Jacobian, which is the linearization of this, which is nonlinear because you see you got a dependent variable that is to the third power and then these two dependent variables that are multiplied together. So let's go over to Matlab and let's do this. So the first thing I'm going to do is I'm going to clear all old variables. Oops. So no, I didn't want to do that. I just want it 1%. Clear our old variables, and I'm going to make it bigger so that you guys can see a little bit better. Okay, so clear all old variables. You do that with clear all command. Then I'm going to define new variables, and I'm going to define those with the sims command, and it's going to be x and y. Now I'm going to define my well, I'm going to find the zeros, or I could just say defining my functions, and I can define the right hand side of those as p of x, y, and I only need one parenthesis, p of x comma y. That's going to be equal to -2 times x times y. Close that, and q of x, y, x comma y, and that's going to be equal to y minus x plus x times y minus y to the third. So now that we have these two, and I'm going to put I put a semicolon at the end because I don't want them to output here when I execute the code. But once we have this, what we can say is finding the critical points. And how do we find the critical points? Well, we need this to be equal to 0, so that's going to have to be equal to 0. And equality is given by a double equal sign in Matlab. And this to also be equal to 0. So I put it over here, has to be equal to 0. We use the solve function, so solve, and then we say that we want to solve for what? For the variable. See, it tells us right here, we need to put the variable. Well, we want to solve for x and y. And then we want the solutions to be real. So we usually put real and true, which only allows real solutions. Then here we know we're going to have two outputs, so we put a square brackets here, and we put x sol and y sol, or whatever name you want to give to those solutions. And let's see what it's trying to say. Best practice, separate output variables with a comma. Yes, thank you for that. And so now what we're going to do is this is going to execute. It's going to find the solutions for x and y. And then from that, we wanted to find the Jacobian. So finding the Jacobian. So there's a command in Matlab which is just Jacobian. You want to put the functions. So p and q. These are our two functions. And let's see. Let's press Control Enter and let's see what we're getting so far. So this is giving us 3 solutions, and this is telling us that that this is not completely working. So let me see if there is. I might not remember how to use the Jacobian. So let me go over here and let me see if I can find a similar script where I used it before. Not this one. Maybe it is this one right here. So if we look at this one, see we have to tell it the function name and the variable name. So that's going to be actually p comma q and the variable names, which are going to be x and y. And so now if we press Control Enter, Well, we forgot a comma here, but it still did it for us. Okay, that's good. So this is our general Jacobian, and we'll call this Jacobian J. Now what do we want to do? Well, remember, now we want to evaluate the Jacobian at each of the critical point, and these are pairs. So this goes with this goes with this, and this goes with this. So let's evaluate the Jacobian at each critical point. And to do that, we use the subs command, and we need to put in the expression, so in this case our J, the old variables, which in this case are x and y, and the new variables, which in this case are x sol 1 and y sol, well, not the new, what you're substituting for the variable, y sol 1, because this is the first entry of this vector. And now another thing that we want to do is we want to copy this 3 times. There is a more efficient way of doing this with a for loop or a while loop. But we can do it this way as well. And here we're going to want to know the eigenvalues of this. So we can use the eigenfunction applied to each one of these. And then once we know the eigenvalues, we can say this is eigen 1, this is eigen 2, this is eigen 3, and from this we can press Control Enter, and it'll tell us what the eigenvalues are. And I suspect that we did something incorrectly, because here it's telling us that the eigenvalues are always 0 and 1, 0 and 1, 0 and 1. And if that were to be the case, then this would be a degenerate unstable case. However, I suspect that, see, we were supposed to change these. So this would be 2, 2, 3, 3. And if we press Control Enter again here, so this has both eigenvalues that are negative. So this is going to be stable. And then this has both eigenvalues that are, well, one negative, one positive. So this is a saddle. And this should be a degenerate unstable case because this is positive and this is 0. So now let's go over to calcplot and see if our analysis is correct. Where's calcplot? Right here. Let's go over to calcplot, and I'm going to show you how to do this. So the first thing that we do is we select vector field. Then we're going to go over here and ask for show systems of differential equations, and we're going to input that system minus 2xy, and here we're going to have y minus x plus xy minus y to the third. And now we are going to ask it to graph it. Then we're going to ask it to use fixed lengths. And then we're going to ask for more vectors. So let's say we want 15 vectors here and 15 vectors here. Okay, so we said there were how many critical points? Well, we have 0, 1. So let's plot the different critical points. Oops, I want to click on point. So we have 0 here, 0, 1, 0. That's going to be 1 point right there. You can see it's a critical point and it looks like it's stable. And what did we say for this one? We said that this one was unstable. So this analysis was incorrect. This looks like a stable point. You see that everywhere we're going towards it. So that's a stable point. and this was the point sorry. I think we're getting things mixed up. 0, 1 is this one. It's the third one, which has 2 negative eigenvalues. So yes, it is stable. Now, if we look at 0, 0, it's here, 0, 0, that's our first critical point. Then we select point, we get 0, 0, even though we know where 0, 0 is. But I just want to make it clear to you. And we go right here. Now, it's hard to get on that point, right? We'll see we're going away from everywhere. We can't really get to that point. So that's unstable. And it doesn't really look like a spiral. And it is indeed, I think, a degenerate case because we have a 0 for one eigenvalue and a 1 for the other. So it's kind of like a limit case. Then we're going to be looking at the last critical point, which is at 0, negative 1, because we already did 0, 1. So 0, negative 1, 0 here, negative 1, that's 0, and I'll do it this color. And this one we said was a saddle. And as you can see, it really does look like a saddle. And this is because we have a positive eigenvalue and a negative eigenvalue. Okay, so I thought this was really useful for me, and perhaps next time I'll show you how to do the gradient. Sorry, not the gradient. The slope field, the face plane in Matlab. And until then, I'll see you next time.